Hello, ladies and gentlemen. It is a pleasure to be presenting to you. Please allow me to introduce myself on behalf of our team. My name is Fito, a research member from the team led by Sir Muhammad. We also have Sir Taufik Rahman, Sir Setiana, and Sir Jamari as our research members. We are all from Laboratory for Engineering, Design and Tribology, Department of Mechanical Engineering, Diponegoro University. On this occasion, I will be presenting you about our research titled A Hydrodynamic Comparison for Thrust Bearings with Surface Texture. These are the outlines that we will discuss. The first one is Introduction. Thrust bearing is designed to support axial load, different from its counterpart, journal bearing, that is designed to support radial load. The tribological performance can be improved by surface texturing. Surface texturing is a feature given to a geometry with certain configurations. The surface texture may improve load carrying capacity and decrease the probability of surface contact. Previous researchers have narrowed down the optimal configurations in which we will use two geometries adopted from previous research. And there are four variables that we have observed: maximum hydrodynamic pressure, maximum temperature, load carrying capacity, and friction force. Moving on to research methodology, these are the details for the geometry. The surface texturing geometries are adapted from the work of Fovlias and others and Henry and others. These consist of parameters for the stator or the pad and the rotor, and also the fluid domain, that is the lubricant. And these are the schematic diagram for the rotor stator. And we take the gap between rotor and stator as a new domain called the lubricant ISO Fiji46. And we also input the thrust color rotor with a rotational velocity of between 1000 and 6000 RPMs with an increment of 1000. These are the spatial discretization process. The left-hand side is the blocking process, which will then be converted into meshing process. On the right-hand side, we used ISM CFD for this process. And these are the governing equations. The first one is mass conservation equation. The second one, momentum equation. Third one, energy equation. The fourth one is McCool-Walter relation, which is used to model our lubricant, the viscosity, as a function of temperature, which will then be translated into piecewise linear as an input to ANSYS fluent. These are the thermophysical properties of the lubricant ISO Fiji46. We define the density, specific heat capacity, and thermal conductivity as an input on ANSYS fluent. And these are the boundary conditions. For the top surface is the fluid rotor interface, a continuity of heat flux and temperature with angular velocity of rotor 1000 to 6000 RPM. The bottom side is fluid bed interface, continuity of heat flux and temperature. The left and right side are called sides with periodic condition. The inner surface as the inlet and the outer surface as the outlet. And these are the results that we have obtained. These four figures are the distribution contour for the lubricant taken at the midplane of the thickness, which is at 10 micrometers. The left-hand side is the pressure and the right-hand side is the temperature. Focusing on the left-hand side, we can see that the maximum hydrodynamic pressure for the single open pocket shown by the red zone is higher than the textured pocket, with a value of 3.81 megapascal at single open pocket and 2.18 megapascal at the textured pocket. The maximum zone occurred at the same place due to pressure buildup that occurs at the end of the surface texturing, and because of rotational activity of the thrust bearing. On the right-hand side, it can be seen that the temperature for the single open pocket is lower than the textured pocket, and the maximum temperature occurs at the trail inside of the outlet, shown by the red area. And these are the distribution plot for the hydrodynamic pressure and wall temperature. As can be seen from the blue lines representing open pocket, it can be seen that the open pocket shows higher hydrodynamic pressure at every point and lower wall temperature at every point also compared to the textured pocket at 6,000 RPM. And we have also plotted the values of the other characteristics from 1000 RPM to 6000 RPM at 1000 increments. It can be seen that the open pocket shows lower maximum temperature at every iteration, higher hydrodynamic pressure at every rotational velocity, which translated into higher load carrying capacity. But the textured pocket shows lower generated friction force compared to the open pocket HD, even more notable on a higher operational speed, although the exception occurs at the 1000 RPM, which is the textured pocket is very slightly higher than the open pocket. In conclusion, the single open pocket generates higher hydrodynamic pressure, which translates into higher load carrying capacity. The temperature value of single open pocket is smaller than textured pocket at every point. Textured pocket generates lower friction force, even more notable at a higher operational speed. All in all, single open pocket shows superior tribological characteristics compared to textured pocket on 3 out of 4 parameters. That is all that I can tell you. Thank you for your attention.